So a while back, Pinkbike ran some really interesting lab testing that compared vibration damping across a bunch of different handlebars. And that kind of raised an obvious question to me, which was, does any of that actually show up when we're on the trail? So I took that question, I took it out into the field. I instrumented my bike with accelerometers and IR sensors, and I found 5 of the most interesting and kind of kooky handlebars that I could on the market, and I replicated that Pinkbike study. The results were definitely surprising, and that's what I'm going to break down in this video. I wanted to get some bars that seemed the most interesting to me and had the biggest potential to ride different than my stock setup. So I got my hands on the 1UP V2 carbon bars as well as their aluminum counterparts, both with the oval cross-section that 1UP does. I also got the Spank Vibracore bars with foam in them to supposedly help with damping. And maybe most interestingly, I got these bars called the Fast Flex bars. This is a bar that has elastomers actually built into it. The last bar I got was this kind of cheap Amazon bar called the 50/50 mountain bike riser handlebar. The idea is this is kind of the baseline or control handlebar against which I benchmark all the other ones. In terms of normalizing setups, these bars are all nominally 800 millimeters, but they actually came in a pretty wide range of lengths, so I cut them down to 800. The rises, unfortunately, are slightly different, but all in the same ballpark. Not much I can do about that. And clamp diameter is all 35 mil. One interesting thing I noticed when cutting these bars down was actually a pretty big difference in wall thickness at the bar end between the 50/50 and the Spank. The 50/50 was about 3 times thicker. So there definitely seems to be a bit of a different level of design and optimization going into these premium bars. So let's talk about the experimental setup now. If you've watched any of my other videos, you know that I've been building out a suite of data acquisition tools over the years. And for this test, I used that data logger that I built. At a minimum, to reproduce the Pinkbike study, we need the same sensor suite, which is that bar and stem mounted accelerometer. So I built up some 3-axis accelerometers. I designed some actually pretty slick accelerometer mounts for the stem and the bar end. The handlebar mount uses an M8 screw to rigidly mount to the hard plastic of the end of the grip. The fast bar has some weird stuff going on around the stem, as well as the oval cross section of the 1UPs. So I had to design a custom mount that actually just mounts to the top of the stem itself. Because I'm testing on trail, there were some additional sensors I needed that aren't required in a laboratory setting. And these are lap triggers. These allow me to trim recordings to exactly the same section of trail across the repeated runs. Since I couldn't find any good off-the-shelf outdoor grade IR beacons, I prototyped my own circuit. Then I designed some PCBs, ordered them, assembled them, and turned it all into a custom outdoor grade IR beacon. Now let's get into the actual test plan and the testing itself. This is the fun part. For this test, I picked a short 8-second section of what I would call typical Santa Cruz trail. It had a small drop, some moderate terrain in the middle, and a few solid braking bumps and holes at the end. Doing really short sections of trail like this is key for this kind of testing because we're trying to pick up on really small changes in setup, and these typically get drowned out if we were recording a full 3-minute trail section. Let's take a quick look at the track now. I did 5 repeats with each bar, so 25 repeats on the section to try to help with repeatability and statistical significance. And the goal is to ride at a casual 75% pace. You can see how consistent my pace was across the different groups with this plot here. And I was pretty consistent. Everything fairly close with some variability that we'll talk about later. I tried to take note of how each bar felt after every run. And one of the big takeaways is I actually could feel a palpable difference from bar to bar, which I really didn't expect because I'm relatively insensitive to bike setup and I've never thought about tuning the feel of my cockpit other than through stem length and bar rise. Here's some of my real-time feedback. Wow. Subjectively definitely feels different. We'll see if it's placebo or not. Feels sick. I mean, you can see them deflecting. Feels fine. Yeah, they feel good. Super fast bumps. These, I don't know if you can see, it's angled way up. These are what feel the worst. And I felt it there on this bar. That's that stinging I felt on the 50/50. It was for sure muted out on the fast. And I think on that 1UP carbon, it's that kind of thing. I think Whistler braking bumps that just destroy your arms. That's kind of where I feel like we might be picking out some real differences, which can add up over the course of a race or day in the bike park. Ooh, interesting. It maybe feels a bit better through here. I don't know. First run, let's do it again. Muted maybe is the word, man. I don't know. It's not a huge difference. After finishing these repeats on a normal trail, I wanted to get repeats on a single big impact event. So I went to a drop that I built with some buddies a few years back and found the courage to hit it 15 times, 3 repeats for each bar. This turned out to be a futile exercise because I ended up abandoning this analysis because the variability of how I landed the drop just so far outstripped the differences that might manifest between bars, at least for this type of analysis. Okay, now let's get to the fun part, which is the analysis and results from testing. So when we're talking about component performance in the field, we're often talking about vibration and how it's transmitted from the trail through the bike and ultimately to the rider at the hands and feet. Before we go any further, I want to talk a bit about the frequency domain because it's hard to do much vibration analysis without it. And basically all this is instead of looking at accelerations with time on the x-axis, like you might be used to seeing, like this plot of, hey, here's my acceleration on this section of trail for 8 seconds. We're looking at acceleration with frequency on the x-axis, which basically is how many times per second something is happening. As a simple example to help understand this frequency domain, let's say we're going through this lovely section of braking bumps and we're hitting 7 of these braking bumps per second. Well, our acceleration might look something like this. It's a really oversimplified plot, but you get the idea. You have these acceleration spikes, as you're seeing, happen every time we hit a braking bump, and there's 7 of them happening per second. So when we transfer this signal over into the frequency domain, what we see is just one big spike at 7 hertz, saying, hey, pretty much all of this signal content, all of this acceleration is happening at 7 hertz. When we're actually out on trail riding, we're obviously analyzing much more complicated signals, but just know the frequency domain is a nice, easy way for us to decompose a signal and see what's going on in terms of vibrations at given frequencies. This is important because we as riders and humans in general are sensitive to vibrations at different frequencies. So something at 10 hertz might feel different or better or worse than some vibration at 20 hertz. In my last video on tire inserts, I go a little more in depth on this, but hopefully this is a good shakedown. Okay, so we can finally get to the results from our actual testing. What you see here is the results from a single run on the 50/50 handlebar, and it's showing the acceleration signal content in the frequency domain like we just saw for those examples. So the purple line represents the acceleration at the stem and the red line represents that at the bar. What we can do from here is divide these two signals. So take the bar acceleration, divide it by stem acceleration, take the square root, and we get this value called amplitude transmissibility. And this just tells us how much of the bar is amplifying or attenuating vibration. Okay, and that's what we've done with this plot here. It is the average amplitude transmissibility across all the repeats done for each bar. And this is computed just in the vertical or the Z direction. I've also computed it for longitudinal and vertical, so in the X and Z directions. And it kind of tells the same story, which you can see here. So I'm just looking in the vertical direction. The very first thing you notice is that it looks like the fast is really doing something different. You see, like, it is the big standout in that kind of 45 to maybe 80 hertz region, and it's really cutting out vibrations in that zone. You know, this is where a lot of handlebars experience resonance, so it's where they kind of hit their natural frequency. And you see that the fast bar is really cutting that out. So putting elastomers in bars appears to actually do something significant. But it's important to note a lot of our signal content is not in this high frequency zone. I'll overlay really lightly that PSD plot we were just looking at, that frequency plot we were looking at, and you'll see, hey, a lot of our energy is actually low, like in the 20 hertz area. But even if this higher frequency buzz isn't dominating the signal, it probably still has an effect on comfort. And I would say in terms of fatigue and injury prevention, probably does something over the course of a stage race, a week at Whistler, and especially, you know, year over year and a lifetime of miles as they add up. So it'd be nice to have a metric that we can use to parse out those differences in the lower frequency zones. And this is where Pinkbike study comes into play. If you remember, they calculated the root mean square, or RMS, of acceleration at the bar and at the stem and divided them for their RMS transmissibility metric. And they just did this for the total acceleration at stem and bar, not broken down by frequency, which actually works great in the lab because they're just testing at one dominant frequency. If you remember, they were pedaling and hitting those little bumps on the rollers at something like 30 hertz. On trail, we actually have all sorts of different frequencies of vibration. So we'll do something a little more complicated by computing the RMS of acceleration in those different frequency bins. So 10 to 20 hertz, 20 to 30, and so on. And that's what you see plotted here. here. A bunch of literature suggests that like 10 to 40 hertz is generally a zone that we want to minimize vibrations in, because humans are sensitive to those in terms of perceived harshness. And so you'll see that, you know, the Spank and the 1UP Carbon and the Fast all seem to be doing well in that 20 to 40 hertz zone. They're all performing pretty similarly in that 10 to 20. And so I guess, you know, elastomers, oval cross sections, and foam in your bars are all doing something ostensibly. The 50/50, as we might have expected, had a little bit higher values in those core comfort regions, but not like that worse. And surprisingly, so did the 1UP Alloy. But if you remember the time plot of how long each section took for me to ride, I did average very slightly faster on those bars, and I had a slightly larger spread of speeds, and that could be influencing things. It's important not to extrapolate outside the bounds of this test. It was one rider, one short section of trail, a few repeats, one day. So I'm not saying one bar here is better than the other. We're noticing the difference that I felt and that I measured within the context of this test. The other thing to note, you know, like we saw in the amplitude transmissibility, similar story with RMS transmissibility, the Fast seems to be doing really well at cutting out that high frequency content. Okay, let's move on to our last metric. In these Pinkbike studies and in the cycling industry in general, you hear a lot about the topic of compliance. In engineering terms, more compliance means you get more displacement per unit force. But I think as riders, we often talk about something feeling compliant as feeling smooth, or something that feels soft, or something that feels good. I'm sure a lot of times it actually maps to the component in question being more compliant, but maybe sometimes it doesn't, and maybe this is where some confusion comes from. For instance, in this test, I perceived the 1UP Carbon bar as feeling pretty compliant or smooth or soft, and we actually learned from the Pinkbike study that it's a pretty stiff bar. You know, but I felt this feeling of compliance. And so what is that? Well, I think one of these plots that I looked at during my analysis might go some way in answering that question. And this is the phase plot. Basically what this is when we go into the frequency domain, we have magnitude, which is what we've been looking at, and we have phase, which basically just tells us how much is the output signal delayed with respect to the input signal. And so you'll see in this phase plot, especially in those low frequency zones where the rider can kind of command motion and is maybe a more active part of the picture, we actually see that there's pretty different timing in terms of the phase lag. And so what I did is computed this average phase lag in this low frequency range, and the units can be converted from like radians, the phase units, to time delay in seconds or milliseconds. And what we see is the 50/50 bar, which I felt had the least compliance, it kind of was like the stiffest feeling or ringiest bar, has the lowest kind of time delay or phase lag. And the Fast bar, which I felt was kind of the softest, or maybe as a rider, most compliant bar, ended up having the most time delay. Closely followed up by the 1UP Carbon, which again, it's like mechanically it's not that compliant, but as a rider, it has this feeling of compliance. And the 1UP Alloy and the Spank are kind of somewhere in the middle. And so maybe what we're seeing in the industry is a bit of a semantic issue here, where we have this kind of engineering term of compliance, but then we just have this like rider feeling of compliance, you know, which might not actually map to this strict definition of compliance, but you know, it's a real thing that we're feeling, and it might map to these kind of different types of performance metrics. And for example, in our case, it's that kind of phase lag idea. I think one of the coolest things from this study personally was just that I could actually go out and feel the difference between bars, because I'm not that sensitive to setup. But judge for yourself if that was placebo or not. Definitely those big swings between like the 50/50 and the Fast made it a little easier to parse. But then it was also cool that I was able to correlate that kind of feeling that I had when I was riding between the bars to actual quantitative results. It's also neat to see that all these different methods that companies are using and implementing to try to make their products better actually seem to be doing something, which is cool. It's not just like marketing fluff. And then the last thing, like, don't go out and buy new crap. I do this kind of out of interest because I'm an engineering nerd and I like to ride. But whatever you're running is probably fine. Like, my bike is clapped and I still ride and it's fine.